So, let's talk about software engineering. We throw that term around all the time, right? But what does it actually mean? Is it just a fancier way to say programming, or is there something bigger going on here?
You know, if you've ever written a bit of code, maybe a little script to automate something, or you built a simple web page, you know that feeling. It's creative, it's intuitive. Honestly, it feels a lot like art. You just kind of build it and fix it as you go.
But here's the thing. When you try to take that artistic, figure-it-out-as-you-go approach and apply it to a huge project, it just completely falls apart. And I mean, look at these numbers from the Standish Group. They're kind of shocking. For big software projects, almost half of them are late or way over budget. Nearly a quarter just get canceled outright. Only about 28% actually succeed. So what is going on?
Well, here's a great way to think about it. You can probably build a doghouse with some intuition, a hammer, and a few pieces of wood. No problem. But could you build a skyscraper that way? Absolutely not. For that, you need blueprints, you need to understand physics, materials, you need a disciplined process. In other words, you need engineering.
So for our first section, let's trace that exact journey. How we went from programming as this free-form art to a full-blown crisis, and why that simple build and fix idea just couldn't keep up.
This build and fix style was really the default in the early days of programming. You just hammered out some code to get something working, and then you'd spend all your time patching up the bugs as they appeared. It's pretty much how you'd code a homework assignment, right? Get it working, then clean up the mess. And for small stuff, hey, it works.
And this chart just says it all. Look at what happens with build and fix as the program gets bigger. That bar for effort just skyrockets. It's an exponential curve straight into chaos and missed deadlines. But the engineering approach, it keeps things manageable, predictable. The effort still goes up, but it's a straight line, not an explosion. So what's the real reason for this?
Well, the answer is so fascinating because it has nothing to do with computers. The real answer is inside our own heads. Let's dig into why complexity is so incredibly hard for the human brain to handle.
So, what is it really? We know the effort blows up, but why? What's the fundamental roadblock that turns these ambitious, exciting software projects into a total mess? The answer, believe it or not, comes down to one single number: 7. That's it. Sounds kind of weird, but this one number is the key to this whole problem. Turns out, cognitive psychologists figured out that our short-term memory, the brain's RAM, can only juggle about 7 things at once, give or take a couple. Once you try to track more than that, you just start dropping things. Your brain gets completely overwhelmed, you get confused, and you start making mistakes. And that right there, that's the big aha moment. This whole software crisis wasn't a technical problem, it's a human one. A tiny program might have, 4 or 5 things to keep in your head. Easy. But a huge system has hundreds, maybe thousands of interconnected parts. No human brain on Earth can track all of that at once. It's just not what we're built for. Okay. So if our brains have this built-in limitation, how do we build anything complex at all? Well, we do exactly what those skyscraper architects do. We create a blueprint. We use a set of principles designed specifically to tame that overwhelming complexity. And in software engineering, it really boils down to 2 main ideas, 2 super powerful principles for wrestling complexity to the ground: decomposition and abstraction. First up is decomposition. This is your classic divide and conquer. You take a massive, scary, impossible problem and you break it down again until you have a bunch of small, independent pieces that you can actually fit into your brain's 7 slots. It's like trying to snap a thick bundle of sticks. All at once? No way. But one by one? Easy. The second principle is abstraction. This is all about ignoring the stuff that doesn't matter so you can focus on what does. Think about it. When you use a map to drive across the country, you're using an abstraction. You don't see every single house or tree because that would be useless information. You see the roads, the cities, the important stuff. Good software design does the exact same thing. It hides all the messy details behind a simple interface. So, how do you know if you've made a good blueprint? We use 2 main ideas: cohesion and coupling. A great design has high cohesion. That means each little part, each module, does one thing and does it really well. And it has low coupling, which means the parts aren't all tangled up with each other. It's the difference between clean, connectable Lego bricks and a giant, messy plate of spaghetti, where pulling on one noodle moves the whole thing. So we have our blueprint, we have our principles. Now let's move on to the next part: actually building the thing with discipline and making sure it works. Over the decades, we've actually come up with different styles for these blueprints. Back in the 60s, it was all about managing the flow of instructions.
Then, in the 70s, the focus shifted to organizing around the data. By the 80s, we got object-oriented design, which tries to model the real world.
Now, the important thing here isn't to memorize the names. The big idea is that each of these was a better, more powerful way to apply decomposition and abstraction. They're just better toolkits for building bigger and more complicated things without our brains exploding. Of course, a huge part of any engineering discipline is inspection. For us, that's testing. There are two main flavors. You've got black box testing. That's like getting in a car and checking if the steering wheel turns the car and the brake pedal stops it. You don't care how it works, just that it works. Then there's white box testing. That's the mechanic opening the hood, taking the engine apart, and making sure every single piece inside is working exactly as it should.
Okay, let's bring this all home. We've gone on this journey from thinking about code as a personal art form to understanding it as a disciplined practice of engineering that basically runs our entire digital world. You can really see the progression, can't you? It starts as an art, driven purely by intuition. Then, with experience, it becomes a craft. But to build the massive, reliable systems we depend on every day, it had to evolve into an engineering discipline based on solid, systematic principles.
And that leads us perfectly to the official definition from the IEEE. The words that really jump out here are systematic, disciplined, quantifiable. It's not about being a lone genius or pulling an all-nighter. It's about a repeatable process with proven principles to build things that work. It's about applying engineering to software.
Which, of course, leaves us with one heck of a final question. We went from art to craft to engineering. But now, with AI starting to write more and more code for us, what's the next stage? What does it even mean to be a software engineer when the machine itself is one of the builders? That's something to think about.